Desk Ladyada.
Hey everybody, and welcome to my desk. It's good to see everyone. We're well into spring and summer, and so I'm not good with plants, but I decided to buy some plants, and I promptly kind of killed it, and it sort of inspired me to maybe do some projects with soil sensing and plant monitoring, because we do stock a soil sensor, but hold on, maybe I'll actually grab it to show it. But we've had some complaints that it's not awesome at soil sensing because it uses uh, the built-in capacitive sensing of the SAM-D10. So let's go to the overhead and I'll show what we've got and what we're working on. So this is, there you go. This is the soil sensor that we stock, and it's not bad. There's nothing wrong with the soil sensor, but it's a low cost. It's like $750 or something. It's an early designed using Seesaw, and it's got a SAM-D10 on there. And the SAM-D10, we use the SAM-D09 on a lot of early Seesaw boards. The SAM-D10 is the same like pinout layout as the SAM-D09. It's a Cortex M0 Plus. It doesn't have USB, but it does run at 48 megahertz, and it has, I think, 32K of flash and maybe 16K of RAM or something. It's actually kind of a nice chip. Runs at 3.3 volts, and it has the 10 version has the capacitive touch Q touch peripheral that the SAMD 21 and 51 series has. And it's, I think like many years ago, we did a reverse engineering stream on the Desk of Ladyada where we showed how we figured out by, I think, not Ghidra, but we ran IDA on the binaries that are distributed for interfacing with the peripheral. We found the register map, and we're basically able to use the capacitive touch element without linking to their library, which is great. So that was called Free Touch, and the capacitive touch sensing works. It detects the capacitive touch of a human salt meat body, and that same capability is kind of okay at measuring the capacitance of wet soil, because wet soil is also kind of like a salty meat body, except the meat is made out of dirt. But the problem is that it saturates very quickly. It's not like a great sense. It's okay, right? It's for under $10. It's good enough for some basic soil sensing and detection. But we wanted to improve this maybe by using maybe first off, I want to get rid of the SAM-D10 because it's a little expensive and the price definitely went up. Microchip raised the prices. I wanted to move to an AT-Tiny chip. I wanted to stemma QTify it. I want to have little, you can have multiple sensors by flipping these switches to change the address. I added a temperature and humidity sensor, so it can do a nice temperature humidity. It's got a filter on top. And because it's using the AT-Tiny series, which runs at 3 or 5 volts, you don't need the regulator or the level shifter. So you save a bunch of, it's basically the same size, but you can tell it's a lot smaller. And, the cost is less because the chip is much less expensive. So Carter has been working on the protocol to use this. And instead of using a single the built-in capacitive touch capabilities of the AT-Tiny, it does also have a capacitive touch peripheral, but we found that also it doesn't work super great with soil. The best solution that he found was to actually use just a 1 mega ohm resistor and use built-in capacitive touch sensing by just doing RC filtering. So maybe I'll Google real fast, see if I can find a capacitive touch. Maybe I can find an image that. Okay, so yeah, this is actually a pretty good from DigiKey. Coincidence. I can go to the computer. So this image, talks about basically the technique that's done is as an RC filter will turn a square wave into a sawtooth wave, and if the R is fixed and the C changes, the higher the C, the more you get a wave effect. Actually, wait, this is, well, it's not exactly the same thing, but the waveform looks right. So as you touch it, the waveform changes, and the speed at which it rises to hit the digital voltage input that's detected by your microcontroller changes, and so it'll change, in this case, the frequency, but it also could change the delay between. There's a couple different ways to measure how the RC filter affects your square wave, by the capacitance added by touching or by soil. So then, so we did that sensor, and then I was like, oh, so Carter's working on that code. Can you go back to the overhead? And then I was actually also like, oh, what would be cool is if we had, and we came up with this idea like years ago, but again, like there was this period of time where I couldn't get SAMD 21E18s. So we took a break from Trinkies, but we did have this idea a long time ago to do a soil sensing Trinky. So it's not really a Trinky. It's kind of like it's just all on one board. It's got USB-C, and the C goes out the end, so that way when you plug it into the soil, it doesn't it's not top heavy, it doesn't have the cable pulling it back. It does have a STEMMA QT port, so you could plug in, a UV light sensor, or this has temperature and humidity, but maybe you want, air quality or CO2 or what have you. You could plug that in. SAMD21E18 can run CircuitPython, can run Arduino wonderfully. Not a complicated CircuitPython, but for basic soil sensing, it'll be okay. This is a 3-volt device, so you needed a regulator up here, and then there's a reset button. Like I said, I added a soil. In addition to soil sensing capacitive sensing element down here, you can see the 2 plates of the capacitor. Temperature and humidity with a filter on, and I tried to put it up top, and then also has a NeoPixel over here and a light sensor, although I'll say the light sensor, it was only 2 cents. It's the AELS PT19, which is a very low cost light sensor, but it's shaded almost all the time, so it's not super useful. But anyways, it's there anyways. So yeah, it can run CircuitPython, can run Arduino. You plug it in, I programmed these boards, and so let's go to Atom. I just unplugged it, so let's see. Okay, it's booting up again. So it's running CircuitPython, and okay, so go to the computer. And so I've been running CircuitPython, and you see this script. This is actually the wrong code. This is the right code. So let's, yeah, every 5 seconds is fine. So this version is just printing out to the REPL, the humidity, the temperature, and the light. If I cover the light sensor, I think I've got the right sensor. No, maybe I have the wrong sensor here. Hold on. Sorry, 1 second. I have a lot of COM ports. COM port. This is confusing. Okay, so let me try again, covering the light sensor. Maybe I have like 2 of these sensors plugged in. Okay, no, I think this is the right one because I just breathed on it and the humidity is going up. Maybe? Because there's this one. I don't know. That's 83 and this is 87. Okay, so when I touch it, I don't know, maybe there's something wrong with my sensing. When I touch it, you see the soil number goes up to 600. And when I let go, it goes down to 30. So it does detect, human capacitive touch about, 0 to 1,000. And then I've got this plant, which is, a little sad plant. There you go. And if I stick this in here, the soil measurement is, about 100. And then if I add some water in the area, let's see if I can moisturize it. You can see the soil wetness goes up. Again, it was like 100, now it's going up to 400 because I just put water like right next to the sensor. So this works okay. I don't know why the light, oh, sorry, I know why the light sensor is broken. It's actually not working at all because on this PCB, I accidentally put the light sensor on. A digital pin doesn't have analog input. And then I blue wire hacked that motherboard, but not on this one. So that's why the light sensor doesn't work. You learn stuff. Okay. So talking to Carter, he's like, oh, yeah, with this technique, though, what you want to do is like plot it over a long period of time. So what I did is this, one second, this board is the one that I'm demoing here, but the one I have for my rose plant over here, I don't really want to grab because it's kind of delicate. There's another plant over there. There's some roses with another one of these soil sensors in it. That sensor has a slightly different code. What that one does is actually has a secondary USB port. So it with CircuitPython, you can create multiple USB peripherals in addition to like the basic one. So usually you have the REPL, and like in this this sensor, it's printing to the REPL. And so if I control C, like, or like send characters, I can break out of the REPL, and then I can like, type stuff in, and I can control D, and it starts again. But if you don't want the REPL to possibly like mess with your code, you can create a new data channel for USB CDC, and it creates a second COM port, and then you write to that COM port the temperature, humidity, light, and soil. And then if you can bounce away to the overhead for a second, because I'm going to delete my key. Okay, so now go back to the computer. Okay, so I deleted my Adafruit IO key. So then I wrote a Python script that I run on my computer, and it's really simple. It just connects to Adafruit IO. It reads the data from the COM port, and it sends that to Adafruit IO. So sensor data from the SAMD21 into the computer via data COM port. I run another Python script. There's like 2 Pythons here. Reads that COM port data and sends it to Adafruit IO. Why? Because I wanted to log it over a long period of time. My computer's like constantly rebooting and like crashing, and I don't want to like try to save it in the COM port history. And also, I want to be able to plot the data. So using Adafruit IO is actually kind of the easiest thing. And this is what you get. So you got the humidity, the soil, and the light. I made a little dashboard with feeds. So the one thing you notice is that, like, for some reason, when I was at my desk, like around this point, like, a couple days ago, like the numbers doubled. I'm not quite sure exactly why, but I was always also messing with the algorithm a little bit. Second, the number slowly rises over time. And like this is, it started out at like 170, and then it like slowly rises up, and it's kind of stabilizing, but it's still up to 300. And then I just like messed with it a few seconds ago, so it dropped down to 116. There's definitely, so there's the theory of like how this works, and then there's the practicality. There is something with I'm trying not to like polarize the water, but like, or maybe there's water that's seeping into the PCB material, or there's some like residual charge. I'm not exactly sure what it is, but like I shouldn't be, it definitely, like, when Carter was working on it, he did this for like, weeks at a time. It rises up slowly, and then it does sink eventually as the soil dries out. And then you do see like this curve of, okay, it's got dry, and then you water it, and then it goes back up again, and then it kind of drifts up a little bit again, and then it sinks down. But I want to kind of avoid that, because I think this makes it difficult to calibrate. And I also think like this weird jump up here, like, I don't know why, was it like touching? Maybe I think the sensor maybe was touching like the metal. It's in a metal plant pot, so that could also, deeply affected it. So what I was looking at is what I call the soil sensing social media network. So this was like, sometimes like a thread. There's a couple threads on the internet which are like, wow, like all knowledge about this like weird esoteric thing is contained in this thread. So there's this like blog spot post from 2011 where some guy is like, oh, talking about like capacitive soil sensing. And he kind of goes through the science of this, and talks about his design and sends it out to Lane's PCB order, which is the predecessor to Osh Park, which I think is really funny. And this is, back in the heyday of like the maker community. And so a lot of people ended up like chatting, and like a lot of folks actually were over the years in like 2016 and 2020, they've been chatting about different techniques. And one thing that's interesting is a lot of discussion ended up kind of chatting about how, like, especially later on, you don't want to actually do what I'm doing, which works okay again, but it does have drift, and it's affected by the salinity of the soil and the salinity of the water and the minerals. What you actually want to do is use a high frequency um, sensor. So instead of, like, I think my square wave coming out of that, I'm using to detect the RC filter is like 10 kilohertz or something, or maybe 100 kilohertz. You actually want it to be in like the 10 to 100 megahertz range. And another thing that I thought was quite interesting is someone made the observation, if you go to the overhead, that this design, even though I have this, the idea is that this is two plates of a capacitor and the soil acts as the dielectric, and it's fine that that it's planar, that it's not a sandwich. There's no requirement, it's as long as you have a dielectric that can conduct between the two plates. But even though there's this gap, the FR4 material is going to absorb water. And so if you look at like commercial soil probes, and like there's discussion about it, they use two metal prongs so that they can't absorb um, water, which I'm not going to use here because, again, I do want to keep this inexpensive. I don't want to have a separate metal prong setup. So one option is, of course, using a aluminum back PCB, which I'm kind of thinking about. That could be interesting to use that as like, one gigantic plane. The other idea is maybe like cutting a slot here. And so that the FR4 in the middle, even though like you might get some water absorption on each leg of the capacitor, you wouldn't, this gap in between that can absorb water, even this large gap, I think if it got wet enough, it could start to conduct, and it might be causing some of that creepage. Although I think the creepage actually is just like the FR4 absorbing through the edges, which is, kind of a challenge. I did see one person mention that they used a inner layer of a 4-layer PCB, but they said that didn't make a huge difference. So I do like the idea of having like a two-prong probe so that you don't get, any cross signaling. And secondly, on the 7021, it's running at 48 megahertz. You can do a 24 megahertz square wave out of a timer pin. Ditto, the AT Tiny can run 20 megahertz on an internal oscillator. You can even actually kind of speed that up, overclock it a little bit. So 20 megahertz, you can get 10 megahertz square wave out. And I want to maybe try that technique. So I might do a little board respin and try that and see if I can kind of minimize this creepage, because I'm a little interested in seeing if I can stabilize the value a little bit. All right, so I went on for quite a while, but then I thought that was kind of interesting. All right, so that's where I am with the soil sensing. And so the other thing I was thinking of is, this will lead into the great search, is, I have these sensors plugged into the plant, but they have to be connected with a USB cable. And I thought it would be kind of cool if it had a standalone mode. So instead of having the data constantly syncing, first off, I could update it to use like an ESP32C6, which first off would definitely generate 80 megahertz square wave. No problem whatsoever. It's running at like 240 or 160 megahertz. So like, you can definitely get massively high speed frequency square waves out of the, but by using the PWM outputs, or the, some of the DMA helper, the RMT probably could generate a high speed square wave as well. But I think even the SAM-21, I could see having like a standalone mode where it like blinks the neopixel, like senses every few minutes and then blinks the neopixel. So I decided to design a version, if you go back to the computer, that has a coin cell on the back. And I would have to like do, you know, a bunch of stuff. Definitely have to make it bigger because the coin cell itself is 20 millimeters diameter. It's a CR2032. I'd have to change the circuitry to allow this to go into a deep sleep mode. And like, I thought I'd widen it to be like 1 inch wide. And then, you know, then these would be the two prongs again. And then this coin cell on the back would be, something that could hopefully run it. I think that especially this ESP32C6, I've gotten it down to like 10 microamperes. It can run for a hell of a long time and then send that data over Zigbee or Bluetooth or Wi-Fi, or, you know, Matter. So I thought that'd be kind of cool. So that might be like the fourth step. I think it's still having a SAMD21 version that's coin cell powered. You can get it down to like 20 microamps, maybe 40 microamps. Still pretty good running off of a coin battery. And one thing that is nice is that, you know, I like the ESP series, but the minute you start using it, the current actually does balloon, whereas the SAMD21 can come up in a lower power mode. All right, so let's go to the Great Search.
Where in the world is that part I need? The Great Search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Thank you, DigiKey. Every single week, Ladyada user power of engineering help you find things on digikey.com. What are you looking for this week?
Okay, so this week I'm working on some soil sensing projects. Oh, it's a green PCB, so it doesn't show up. And I was just chatting about how I wanted to make a low power version. The current version I have plugs into USB. I want to make a lower power version that runs from a coin cell battery, but I couldn't just use any coin cell battery holder. So let's go to the overhead and the computer, and I'll show my dilemma. So traditionally what I use for coin cell holders is this very inexpensive metal, like bent metal plate that goes around a PCB. You can slot the coin battery in. It's very inexpensive. They work really great. But what you have to do is have this big, because the bottom is the contact, it's great for boards where you have a single side that doesn't have any you can't have any traces underneath here because the ground will short to it. And so as I was designing this PCB, I was like, oh, you know, can I use hold on. This is what it looks like. I wanted to use this coin holder, which, you know, would be very compact and inexpensive. But the problem is that there was no way for me to fit it in without the USB, the pads of the USB, or this chip. I'm going to have a lot of traces routing around it, and they're going to have to go underneath. There's no way I can route this whole thing to be single layer just because the pins have certain functions. So what I decided to do is, instead of using this inexpensive bent metal style, is find one that is SMT, because I want to pick and place it on the opposite side, but is fully enclosed and doesn't, like, it's okay that it doesn't use the PCB as the secondary contact. And we covered the inexpensive coin battery holders before on the Great Search, but not this particular type. So let's go to DigiKey, and we're going to go look for battery holder. I'm going to have a sip of coffee. Always helps. Okay, so battery holders, clips, and contacts. Yes. Yeah, lots of options here. Many of these are, again, low cost little metal bits. So we want something for CR2032. Why? Because our microcontroller is going to draw, you know, when it's running, it draws 10 to 20 milliamps. You really do want to have 2032 that can provide that sort of drain. You know, there's a CR 1220. Those are good for real-time clocks, but you can't really run a microcontroller on them. Like, you really, the amount of current that a coin, and we've covered this on like many other videos, the amount of current that you can draw from a coin cell is approximately 1/10 C, which is the milliamp hour rating of the battery. So the battery, a CR1220 is, I think, like 25 milliamp hours. So you can't really draw more than like 2 or 3 milliamps. whereas a CR2032 is about 200 milliamp hours, so you can draw about 20 milliamps from it without a big degradation. So also it's very inexpensive. You can buy CR2032s everywhere. So let's do that. So we've selected it. Number of cells, I don't know, 1 or 2. I'm not planning on doing more than 1, but just want to make sure that I get all the holders. I want them to be active. Okay, so let's see what we've got down here. So yeah, a lot of these like inexpensive bent metal through hole style, SMT style, wonderful and everything. But again, this is, I always love these. These are cute. I've never had a use for them. They're like, they stick up. Very adorable. This is a little plastic holder. I want something like this, but surface mount. This is through hole, through hole, through hole. So like this, but surface mount. So let's take another look. So we want PCB surface mount. Yeah, no PC pin, no wire leads. So let's do that. Apply, and then let's look for ones only that are in stock. I don't really, these, almost all of them are in stock, so I'm not really too worried about it. Good. So these are starting to look nice. The only thing is there's no way to really, I don't think you can really, there's retainer versus holder, but I don't know if I trust. I don't know. I guess it seems like holder really is a holder, whereas retainer requires that PCB. So maybe I'll save myself. Yeah, I'll just do the style holder. Let's look at that, see what comes up. Okay, good. Yeah, these are, now we're talking. Yeah, this is the stuff. Lot of makes and options. Some of these look like they're kind of this, you know, this one. I've actually used these, by the way. These are very nice. I don't know if I'll use it in this case. They're a little bit more expensive, but they're like really strong, and you have to press the button to push the coin battery out. And it's a very satisfying thing to do. MPD always makes really great coin battery holders. Okay, so this is nice too. Wow, 2-cell, because yeah, it has the thing that comes over the top. Okay, but the next thing I want to do is some of these come in tray, and I don't want them in tray or bulk because I need to be able to pick and place them. So let's make sure that they come in cut tape or tape and reel. And then 2025. I really want the 2032. Let me see. Make sure I get the one that, because there's different families. Okay, looks good. So a lot of options. So what I'm going to do is I'm going to just sort by price and then see what's up. So I did actually, one thing I kind of liked is that this was yeah, there's the battery, but it's slim style. And again, the pricing is really good. Like 40 cents in quantity is a good deal. Again, you know, there's something to be said for these like all-in-one fully enclosed style. But I thought I would start with this one because I am pretty price conscious. And like I do want to have, you know, I want to make sure that the pricing of this board isn't too expensive. So I'm going to start with this one, and you can see I kind of already did the layout here with the 2 pads. You can see it's got that cutoff shape. And then, you know, it can go like this. Actually, I think I was like, this was what I wanted to do. Because that way this didn't block the mounting hole. So if we know if we're not done with the battery, it doesn't matter. But also the battery slips past the mounting hole as well. So you can, if you do want to use it, the holder won't be in the way and the battery won't be in the way. And it fits kind of nicely in the back, and then you can pop it up. Another nice thing about the holders versus the retainer style is that the battery comes up the front. So it's, you know, you don't have to worry about like, oh, if I have something in the way and the battery isn't removable. So this is my pick for the Great Search. It's a lovely battery retainer.
Where in the world is that part I need? The Great Search with DigiKey.
And that's Jessica Ladyada. Thanks
Okay,
for
a
joining us.
little bit long, but I
Okay.
think, I don't know, covered a lot. Maybe
Good
if you
stuff.
guys have a soil sensing know-how beyond the basic capacitive touch style, you know, put them in the chat. I'll check them out.
Bye.
Bye, everybody.